Section 7.6, Discontinuous Forcing Functions. In this section, we want to develop a systematic way to handle discontinuous forcing functions using the method of Laplace transforms. To begin, let's define the unit step function u of t as the function that is 0 when t is less than 0 and 1 when t is greater than 0. It doesn't really matter how we define it exactly at 0. Some books will make this an or equal to inequality. For our purposes, it absolutely does not matter. The idea here is that the unit step function, you can see why they call it this, is it's a function that is 0 and then it takes a 1 unit step up at time 0 and then it stays at 1 forevermore. You can think of this as a switch that's turned off until time 0, and then at time 0 it's instantaneously turned on to a value of 1 and it stays on forevermore. Now we may want the switch to turn on at a different time, maybe turn on at time t equals a or be activated at time t equals a, and so we would just use a shifted unit step function. U of t minus a is 0 until for t less than a, and then 1 when t is greater than a, and its graph would look like this. So unit step functions allow us to describe piecewise defined functions very efficiently, and as we'll see in a few minutes, in a way that's very useful for calculating Laplace transforms. So let's practice this just a little bit. Suppose we had the piecewise defined function f of t is 0 if t is less than 1, it's 2 if t is between 1 and 2, and it's 1 if t is greater than 2. So I have the graph here to help visualize this. Just think of this and reading it from left to right. It's a function or a signal that is 0 until you get to t equals 1. At t equals 1, it jumps up to 2. It stays at the value of 2 until you get to t equals 2, and then it jumps down to the value of 1, and it stays at 1 forevermore. So if we wanted to write this in terms of unit steps, and we'll just do this right here on the screen, is we just want to think in terms of switches and what we want to turn on and what we want to turn off as we move from left to right in the graph. So we could, visualizing that graph, we have f of t. What do we want to have happen? Well, we want it to have the value of 0 until we reach a value of t equals 1. So in other words, we want a switch to turn on at time t equals 1. So we'll do u of t minus 1. That will give me a switch that'll turn on, and when it turns on, it has a value of 1. But we don't want it to have a value of 1. We actually want it to have a value of 2. So we'll just multiply this by a 2. And I usually write it in this order. Turn my switch on and then make it be on what I want to have on. And I want to have a 2. Okay, so now there's a 2 on, and when I get to t equals 2, I want to turn on a new switch. So I'll do plus u of t minus 2. This is going to activate a new switch that kicks on. You have to remember, the old switches stay on. There's nothing turning them off unless you turn them off. So here, if I have a u of t minus 2 that starts at time 2, what value do I want it to have? This might seem a little awkward, but watch how I'm going to think about this. In order, I know that I ultimately want to turn on a value of 1. That's what's showing in the graph here. But if I just put a 1 right here, this switch is still on, so this 2 is still on. And if I write a 1 here, I'll actually get a net result of 3, and that's not what I want. So a very useful way to think about this is when you have a switch that's on and you create a new switch, the first thing you should do is zero out what was already on so that you're starting fresh at a 0 value, and then you can add on what you want. So for example, this has a switch value that turned on a 2, and that 2 is still on. When we get to here, we're going to kick on a new switch. Why don't we undo what was already on? So if a 2 was on, I want to subtract off that 2, and then I want to add back, so I'm back to a net value of 0. And now I want to add back on what is the value that I want to turn on to the right of 2. I want to turn on a 1, so I'll add a plus 1. Now I know that this is, we could have written this as just a minus 1 here, but this mentality is something that's very useful in breaking down piecewise defined functions and writing them in terms of unit steps. And now let's just check this. If we were to rewrite, now of course we could simplify this if we want to. You know, we could rewrite this as a 2u of t minus 1, and then here we get a net result of minus 1, so we'll just say minus u of t minus 2. And now let's just check this. Think about this. As we go from left to right, when t is to the left of 1, this switch is off, and this switch is off, so this is a value of 0, and that's what we want. To the left of 1, we want it to have a value of 0. Now think about when we get just to the right of 1, this switch turns on, and it will kick on a value of 2. That's what we want. This switch is not on yet if we're just to the right of 1. It still has a value of 0, so that'll give us a 2. Now think about when we get to the right of 2, this switch is still on, gives us a value of 2. This switch is now turning on and gives us a value of 1, but it's multiplied by a negative, so we get a 2 minus a 1, which gives us the net value of 1 that we want, and that value will stay on forevermore, and that's what this function required, so that's what we do. So this just gives you a little bit of a practice in rewriting a given piecewise defined function in terms of unit step functions. It might be helpful to visualize the graph, but after a little bit of experience, you'll be able to go just from here just to here. Why don't we try one more? One that's not piecewise constant, that has some non-constant pieces to it. But we're still going to play the same game. We get here and we say, well, our function is 0 to the left of 0. We see that there is a switching event that occurs at 0, and at time 0, we want to kick on the function t. So we'll say f of t is, I want a switch that turns on at time 0, and when it turns on, I want to turn on a value of t. That value should stay, that switch should stay on, and nothing's going to change until we get to our new switching moment, which is at 2. So I'll create a new switch that occurs. I'll add a switch that turns on at 2. Let's keep with our lesson from before, is when we write a new switch, we want to begin by turning off what was already on. So we're starting at a fresh value of 0. So I want to turn off what was already on. Now I'm to a net value of 0. But looking at my function, I don't want to have a net value of 0. For example, if this were a 0, I would stop right here. I've zeroed it out. That's exactly what I want, and I'd be done. That's not what this function has. It has a value of t squared when you're to the right of 0. This term just zeroed out what was on before, and now I want to add the t squared to get the new net result. And we could multiply that out and maybe simplify or collect some terms, but this is good enough for our purposes. Now, a very important sidebar conversation we should have is some of the things that how the way I'm going to explain them in this section is a little bit different than what is the way the book explains them. And so we want to take a look at that and have a conversation about that. Now, the book will write things in terms of unit steps sometimes, but it will also use the rectangular window function. So let's define what I mean by that. The book defines the rectangular window function by, this is a big capital Pi of a comma b, and it's a function of t. And it's the function that's defined to have a value of 1 if t is between a and b, and it's defined to be 0 everywhere else. That's an a. So it's between a and b, it's turned on with a value of 1, and everywhere else it has a value of 0. And the reason they call this the rectangular window function is if you think of its graph, it's a function that's 0 until you get to a, and at time a it kicks on a value of 1. It stays on until a time b, and then it turns back off and gives you a value of 0. So you can see this is like a little rectangular window. 0, then non-zero, and then back to 0. Now notice we could rewrite pi of a comma b, or the rectangular window function a comma b. Notice that this is just u of t minus a minus u of t minus b, and that's because, what does this do? Think back to what we were doing just a minute ago. We would want, if we were going to write this in terms of unit steps, we would write we have a switch that turns on at time a, and when it turns on, it should kick on a value of 1. That's what that term does. Then we would have a new switching event, so we would say plus u of t minus b because it turns on at time b, and when it does, it needs to give us a net value of 0. In other words, it only needs to undo what was already turned on. And if a value of 1 was already turned on, we would multiply our u of t minus b by a negative 1. And here we've just written it on the front instead of the back. And notice this is just a way to represent the rectangular window function. Now in the homework, they could ask you, and there'll be different times throughout the course, but in the homework, they're going to give you a piecewise defined function and ask you to write it in terms of unit steps. In the few exercises in the textbook, they're going to make you write it in terms of rectangular window functions. This isn't a really big deal. I would try it both ways. We're going to practice it here in just a minute. Try it both ways. I tend to not use the rectangular window function for reasons that will become apparent as we keep going. I have no problem with using the rectangular window function. It's totally correct. I just don't know that there's any great benefit from doing it. But you can try it both ways, and if you like to use the rectangular window function approach, I think it's about the same in terms of how much work and writing it takes you to do, then feel free to do so. But I do want to discuss it because there are some homework problems in my lab that require you to write functions in terms of unit steps. So we have to practice it at least a little bit. So let's practice writing a given function f in terms of the rectangular window function as well as just in terms of unit steps. So here's the function we had just a moment ago, and we already wrote it down in terms of unit steps using the switching on, switching off idea. And so here's our answer. So now let's practice using the book's approach to write this function down. And one of the upsides to this approach is, remember, the rectangular window function already has the on and off built into it. So here it just turns the function 1 on between A and B, and it already has things turned off to the left of A and turned off to the right of B. So look how that comes into play here. So here we have a function that's 0 to the left of 0, so nothing's happening. And then on the interval from 0 to 2, we want to turn on the function t. And so the rectangular window function, we just want to have it turn on at time 0, turn off at time 2. And what function do we want to turn on? We want to turn on a value of t. So notice this already has the turning off built into it. Now, one thing that you have to deal with rectangular window functions is if the given function doesn't stay off at a value of 0, you have to compensate for that. So notice this function just doesn't stay off when you get outside of the when you get to the right of 2. It needs to turn on the function t squared, and it needs to stay on forevermore. And notice the rectangular window function isn't really built to do that. It's built to have things off and then on and then off again. It's not built to just keep things turned on. And so we just have to go back to the unit step concept. And this is one of the reasons why I don't think that the rectangular window function is perhaps worth any of the trouble, is because oftentimes you're going to have to write things in terms of plain unit steps anyway on the other side of the rectangular window function. So you might as well have done it the whole way in terms of unit steps, but it's okay to do it with the unit steps and a mixture of rectangular window function and a mixture of unit steps. It's totally fine. So this extra term is, remember, this has turned the function t off at time 2. And then to the right of 2, we want to have a new switching event, and we want to turn on the function t squared. So you can't write it totally in terms of rectangular window functions. You do have to have this added term. Now, if you wanted to decompose this totally into unit steps, you would just use the definition. Remember, the definition of pi AB is u of t minus a minus u of t minus b, whole thing times whatever I'm turning on. So the parentheses are very important here. And when we distribute this and recollect terms, we get this, and notice this formulation, which we got from using the rectangular window function approach, is exactly the same as what we got when we did this with unit steps from scratch. So just try it both ways. So back to Laplace transforms. Let's take the Laplace transform of the unit step that turns on at time a, so the Laplace transform of u of t minus a. Now from the integral definition, this is the integral from 0 to infinity of e to the minus st times u of t minus a dt. Now the good thing about this being a unit step is this function is 0 to the left of a, so we can split this inherently piecewise defined function up into a part that's 0 from 0 to a and a part that's 1 from a to infinity. And that means that this part of the integral comes out to be a 0. We do get an improper part, so we'll set up the improper integral as a limit of proper integrals. We'll anti-differentiate, evaluate between limits, and then we will impose the stipulation that we want this limit to exist. We want this improper integral to converge, and in order for that to happen, our s has to be positive. When s is positive, this becomes a decaying exponential term. It goes to 0, and we end up with, after the algebra dust settles, e to the minus as over s with the stipulation that s is positive. So now we've just entered a new Laplace transform formula into our table. The Laplace transform of u of t minus a is e to the minus as over s. So let's highlight that. We'll call that equation 1. And now, whenever we have to realize that whenever we add anything to our table, we really get a 2-for-1 special, because when we learn a new forward transform, we've also learned a new inverse Laplace transform. So we can also say that now we know that the inverse Laplace transform of an e to the minus as over s is u of t minus a. So this, remember to read this both ways so that you get both pieces of information. So let's practice this. Let's find the Laplace transform of this piecewise defined function that's 0 if t is less than 1, it's 2 if t is between 1 and 2, and it's 1 if t is to the right of 2. So first we will practice writing this down in terms of unit steps. So once again, this is a switch that turns on at time 1, and when it turns on, so u of t minus 1, when it turns on it has a value of 2. Then we want to add a new switching event at time 2, and when we do that, we need to turn off what was already on and then turn on the new result that we want. The net result is this, which we can rewrite as this. And now we've written our f in terms of unit steps, so now we're prepared to take the Laplace transform of f. So we won't use the integral definition, we'll use our newfound table entry. The Laplace transform of f must be the Laplace transform of this. But now using linearity, I can break this action of the Laplace transform up over the subtraction, and I can factor out constants. And now this is in my table. I just go back to equation 1. The Laplace transform of u of t minus a is e to the minus as over s. So this Laplace transforms to e to the minus s over s, and this Laplace transforms to e to the minus 2s over s. So that was a very quick calculation that we could do. As soon as we write it in terms of unit steps, we very quickly can get the Laplace transform of the functions, and that's one of the benefits of writing things in terms of unit steps. Now, some other properties or new theorems that we want to add to the list is there are two flavors of this theorem. One is, I think we'll look at the second one first, although when we talk back through them, let's at least talk about number 3 first, and then we'll go back to number 2. Is think of this as we've already found the Laplace transform of u of t minus a. So the question is, what happens if you have a u of t minus a and it is multiplied by a function? That's a very common situation. We've already seen when you have u of t minus a that are multiplied by functions. I realize this is a constant function, so it makes it a lot simpler. But if you go back and you look at our examples, we had unit step functions that were being multiplied by functions. Unit step functions being multiplied by functions. And so this is going to be a very useful property to know how to Laplace transform things of that type. So we think of it like this. What happens if you have a unit step function that is multiplied by another function? And there's really two cases. What if the shifts, I'm calling this the shift, what if the shift in my unit step doesn't match the shift in my multiplying function? And what if I just get lucky and it does match? So let's talk about the easier case first. What happens if the shifts match? If the shifts match, you can apply the definition of the Laplace transform, the integral definition of the Laplace transform, and this comes out to be e to the minus as times big F of s, where big F of s is the Laplace transform of the unshifted little f. We're going to work some examples in just a second. So when the shifts match, this is the new table entry or theorem that you get. We'll call this equation 2. And then what if the shifts don't match? If the shifts don't match, then you still get a multiplication by an e to the minus as in the s domain. But then you get the Laplace transform of g of t plus a. And this is just a result of applying the integral definition. We'll call this equation 3. So let's look at an example. So let's take the Laplace transform of t minus 1 quantity squared times u of t minus 1. So notice we can see that the shifts here do match. There's a shift of 1, a equals 1. They do match, so we get lucky here. And now we just want to think about what is, so we go back to our theorem right here. We need to know what our shift is. We do. Our a is 1. And when the shifts match, our a is 1. And so then we know we're going to get an e to the minus as, but then we need to calculate the Laplace transform of the unshifted little f. So we need to visualize the unshifted little f. So just think of covering up the shift. This would be a t squared. I know there's not a lot of work to write down here, but I'm trying to show you my thought process as much as I can so that when you read back through this and you're even showing your own work, you can think back through these in a systematic way. So I think of this as, okay, I need to know the Laplace transform of my unshifted little f. So this is my shifted little f. I'll cover up the shift, view this as a t squared. I can forward transform that using my basic table to get 2 over s cubed. And now I know the Laplace transform of my unshifted little f. And so I get from equation 2 e to the minus 1s times 2 over s cubed. That was pretty straightforward to do. A little bit more challenging is what if the shifts don't match? So suppose we have a Laplace transform of something like t times u of t minus 2. We see we have a shift of 2 here, we have no shift here, so the shifts don't match, so we're using the g version of our theorem, equation 3. So the way to think through this is we have to spot what our shift is. Our shift here is a equals 2. And now we need to calculate the Laplace transform of g of t plus a. So now when we go to do that, I'm thinking of, if I'm going to find the Laplace transform of t plus a, first I need to get my hands on what g of t is. Well, g of t is just t. My a is 2, so g of t plus a is g of t plus 2. Well, if g of t is t, g of t plus 2 must be t plus 2. And the Laplace transform of t plus 2 is, using linearity and our basic table, 1 over s squared plus 2 over s. So this is my Laplace transform of my g of t plus a. So I'll put it here, and I know it's being multiplied by my e to the minus 2s. So that's my final answer. All right, let's try one more. If we take the inverse Laplace transform of, now this time we'll practice some inverse Laplace transforms instead of forward Laplace transforms. So remember, every time we get a new forward Laplace transform formula, we also get, if we read this from right to left, we get an inverse transform formula. So this is very, very helpful to us. So let's practice calculating the inverse Laplace transform of 2 e to the minus s over s cubed. So in order to use these theorems, we need to set them up, if we're going to read them from right to left, we need to set them up where we have an e to the minus as factored out of our big F. So what I want to do here is factor out the e to the minus as part, so the e to the minus s part, see what I have left, and now I'm looking at equation 2, but I'm reading it from right to left. When I do that, I can see that my a here is 1. This is playing the role of my big F of s. If this is my big F of s, then according to my theorem, what I need to do when I inverse transform, I know I'm going to get a u of t minus a, but I'm going to get f of t minus a, and little f is the inverse Laplace transform of big F. So I need to find the inverse Laplace transform, what little f goes with this big F. This is something we've been practicing in chapter 7. So here we just say, well, if this is my big F of s, then my little f of t must be t squared. But the theorem, equation 2, demands that I do not f of t, but f of t minus a. So if this is f of t, then this is f of t minus a, and I just put those things together. F of t minus a times u of t minus a. And this would be my new inverse transform for this function. And take a moment and look at this. We've never inverse transformed things that looked like this. This is a new type of function that we're inverse transforming, and we're really expanding our repertoire by having added these theorems involving unit step functions. As another example, suppose we had e to the minus 3s over s squared plus 4. Again, I want to factor out the e to the minus 3s, not out of the inverse Laplace transform, just I want to break these pieces up and have this e to the minus 3s on the front, because now it looks like an e to the minus as times a big F of s. I see that my a is 3. This is my big F of s. My big F of s I'll write down here. So I need to inverse Laplace transform this to get little f. In order to do that, it needs to match the things that are in my table. In order to match the things that are in my table, the little b's must match. So I really need a 2 here. I can't just write a 2 here because there's not one there, but I can write a 2 there if I offset it by multiplying by a half. So I'll rewrite this as this so that my little b's match, and I'll inverse transform this. This inverse transforms back to a sine 2t. I'm still multiplying by this 1/2. And now to finish it off using equation 2, I need to find my shifted little f, so f of t minus my a. So that's 1/2 sine of 2 times t minus 3, and the parentheses are very important. So using equation 2, we get f of t minus a times u of t minus a. We just found what my f of t minus a was, and this is u of t minus a. So this is the inverse Laplace transform that we were after. Now let's bring this back to bear to differential equations. So if you remember in the last section, we left off with an example. So I'll just recall we had y double prime plus 4y prime plus 13y equals g of t. G of t, if you remember, was this piecewise defined function. We had 0 initial conditions, and we were trying to solve this initial value problem using the method of Laplace transforms. So I'll just go through this really quickly. We did this all in the last section. We had to do this from scratch because we had no other method for calculating the Laplace transform of this piecewise defined function. We just used the integral definition, took the limit, and we took the Laplace transform on the left, we took the Laplace transform on the right. Here's the work that we had to do to calculate the Laplace transform of our g function. And then we knew how to take the Laplace transform of the stuff on the left. We use our derivative theorems. We apply our initial conditions. We isolate for big Y of s. And then if you remember, we got to this juncture and we had to just stop because last time we did not have an idea about how to inverse Laplace transform this. But now we do. Remember, partial fractions does not apply to this as it stands because it has an exponential term in it. So how can we tackle this? Let's do exactly what we were doing in the last two examples for inverse Laplace transforms. So we know we want to take the inverse Laplace transform of this side. We know we want to take the inverse Laplace transform of this side in order to recover little y of t. The question is, how do you take this inverse Laplace transform? And we're going to start just like we did in our last two examples. In order to use our newfound theorems, we want to pull out this e to the minus as term off to the side and look at what our big F of s is. Now keep in mind, we know we can use our newfound theorems as long as this big F of s is something that I know how to inverse Laplace transform. And we do know how to inverse Laplace transform this. You were practicing this in section 7.4. We'll just do a partial fraction decomposition on this. We will calculate the inverse transform after we do a partial fraction decomposition. So let's just go off to the side. We'll do this. We'll do it in bright blue so that we kind of keep our train of thought separate here. So we'll just grab this big F of s. We see that this is a distinct linear factor. And if you rewrite this using completing the square, we've done this. This is an irreducible quadratic, so we want to write it as a sum of squares. When we write it as a sum of squares, remember we want our numerator to be a table-friendly, Laplace transform-friendly general linear function, so we write it as this would be a over s, and this would be b times s plus 2 plus 3 times my c. This is going to set things up to be easier for us to inverse transform using our table. So now this is all standard fare here. We just multiply by the common denominator. We use the cover-up method or the value substitution method to pick our values. We know we're going to have to pick 3 values because we have 3 constants. When the algebra dust settles, we find these values for a, b, and c. I think we know how to do that by now. And so that gives us the partial fraction decomposition. This is the form. It has this form that is table friendly. I don't know why I rewrote that same line again, but now we'll just substitute in the values for a, b, and c. A matter of fact, I'll wait and I'll substitute them. I know what a, b, and c are, and these are a little bit of messy numbers, so I'll just hold the placeholders a, b, and c, and then I'll say, okay, well, we know that we can factor out the a here. We can split this into a b times s plus 2 over s plus 2 quantity squared plus 3 squared. That's what we've always done. In this case, 3 of partial fractions. And then we know We'll pull the c out. We'll leave the 3 because we want these to match. And this is very amenable to inverse Laplace transforms. So we know how to play the game from here. So let's go back to what we had written in black. Let's go back up here. We were at this stage. And now in order to use our newfound equation 2, this big f of s needed to be something that we know how to inverse transform. So let's pick up that train of thought here in black. Little y of t is the inverse Laplace transform of this. But this in parentheses is the same as this. We know the values of a, b, and c. And so this is our big F of s. Let's go ahead and inverse transform our big F of s to recover our little f of t. Just stay with me here. So we're going to get a capital A. This inverse transforms back to 1 from our basic table. Plus, we're going to have a b. Stare at this. This inverse transforms back to, remember, this looks like a shifted version of a cosine 3t. The shift here is a minus 2, so a shift in the s domain corresponds to multiplication by an exponential in the t domain, so we're going to get an e to the minus 2t times a cosine 3t. And for this term, we have the c pulled out. We see that our little b's match. This looks like something that inverse transforms back to. It looks like a shifted version of something that transforms back to a sine 3t. And because the shift is a minus 2, we get a multiplication by an e to the minus 2t in the t domain. So we very quickly are able to go from big F of s to little f of t. But remember what our theorem says. Our theorem says if you want to take the inverse Laplace transform of an e to the minus as times a big F of s, what it inverse transforms back to, this is equation 2, it inverse transforms back to little f of t minus a times u of t minus a. Well, I have my little f in my hands. I have my a. So this is just, I'm going to rewrite it like this because little f is going to be sort of long here to write. So I'll just flip-flop the order on these to give myself room to write here. My u of t minus a is u of t minus 1. My f of t minus a is I just need to take this f of t and replace all the t's with t minus 1s because my shift is a 1. And if I do that, keep me straight here, this becomes a t minus 1, a t minus 1, parentheses are important, t minus 1, t minus 1, parentheses are important. And then last but not least, I need to substitute in the numerical values. I knew what a was, I knew what b was, I know what c is. And so at the end of the day, what we get is that the solution to the initial value problem is the unit step times this entire function. And if we zoom out from this just a minute, this is our first example that we've encountered where we solved a differential equation or an initial value problem with a forcing function that we could not have solved using our previous methods. In the first few examples that I gave you for Laplace transforms, I purposely picked things that had forcing functions on the right-hand side that we could have done with undetermined coefficients or variation of parameters, just because I wanted to keep problems that were a little bit simpler, and also to compare and contrast the methods that were the new methods with the old methods that we'd already learned. But we're breaking new ground here. We would not have been able to handle this function using undetermined coefficients or variation of parameters. So this is where Laplace transforms can shine. I know that it may have been a little bit algebraically messy, but if you zoom out, what's the hardest thing that we did here? We forward transformed, and really we did this from scratch. But notice, this is just a u of t minus 1. And now, if we were to take this problem, take it from the top here, and we wrote g of t as u of t minus 1, we would have just gone straight to our newfound formula and written this as e to the minus s over s, and wouldn't even have had to have done this. But we do have to take the Laplace transform of both sides. There's no way around it. We're going to have to confront the partial fractions, which isn't too bad. And then we're going to have to be fluent in using the various theorems that are in our table and the entries in our basic table to be able to inverse transforms things like this to get this, and then apply our new, in this case, equation 2 in order to get the solution to the initial value problem. And you can even tell by looking at the form of the solution this form of a solution with a switch in it is nothing that we had seen from doing undetermined coefficients or variation of parameters. So this is our first real example of something that, of an initial value problem that we could not have tackled by our old methods, and we're seeing that we're expanding our repertoire, and as we move forward in Chapter 7, our goal is to keep adding things to our Laplace transform table or list of theorems that allow us to tackle an ever wider set of initial value problems that have features in them that we could not have handled by our old methods. And in the homework, you'll get lots of practice doing that.